Titrations, important from the qualitative perspective for the A-levels. What are the shapes of titration curves? What are the important points of titration curves? And what are appropriate indicators? I will throw in a couple of little extensions to that just to, I hope, add emphasis to the important points. So here's a beautiful titration curve. Obviously, we start off with an acid, 100 mils of it, titrate it with 0.5 molar NaOH, and so the pH goes up, goes up, goes up, swoops up through the equivalence point, and then to where you're just adding more base. First thing to notice is what kind of curve is it? We know that it's a strong base. What can we tell about the acid? Well, the first thing I would look at is I would say this equivalence point here has a pH greater than 7. It's right around about 8. So that means that it is a weak acid. And that's really, really important to notice right from the start. So anyhow, let's look at the possibilities. Phenolphthalein would be a suitable indicator for the reaction, where you want the indicator to change color right around the equivalence point. Phenolphthalein changes right around 8, so it would be a perfect indicator for this reaction. Solution after 50 mils has been added as a buffer solution. Well, when you neutralize a weak acid, you make its conjugate base. So somewhere between about here, once you've neutralized enough of the acid, all the way up to about here, where you've still got enough of the acid left, is going to be a buffer solution. So that looks perfect. pKa of the acid is 4. Well, if it is a weak acid being titrated with a strong base, the half equivalence point is going to have a pH equal to the pKa. That's one of the really, really important places on a titration curve. So here's our equivalence point at 20. So the half equivalence point is at 10. And the pH at 10 right here, this is the pKa, is certainly not 4. It's significantly less than 4. It'd be a little bit less than 3. Now finally, the initial concentration of the acid is 0.1. We're assuming that's correct because we're only looking for one incorrect statement, but always check things. So let's see what we know. Well, we know that we're taking 100 mils of the acid with 0.5 molar NaOH, and we know the equivalence point is 20 milliliters. Okay, at that equivalence point, the moles of acid is the moles of base. Okay, well, we take 100 mils of the acid, but we don't know its concentration, and volume times concentration is moles. For the base, we do know that we had 0.5 molar NaOH, and we know that to get to the equivalence point, we needed 20 milliliters, 20 cubic centimeters. So multiplying all that out, the concentration of the acid is indeed 0.1 molar. So pK of the acid, certainly not 4. That is the incorrect statement. So, two ways to do this question, two ways to think about it. First of all, phenol, Ka 1.05 times 10 to the minus 10. That tells us it is a weak acid. We're then neutralizing it with sodium hydroxide, which is a strong base. And we're asked about the pH of the resulting solution. Okay, well, first thing I would do is I would say, let's figure out what these new diluted concentrations are. For the phenol, we started with 0.5 and 100 mils of it, but then we added another 100 mils to the new volumes, 200. So the new concentration of phenol, 0.25 molar. Same idea for the sodium hydroxide. Start with 100 mils of 0.5, but now that's a total volume of 200, so again 0.25 molar NaOH. So these have the same values, which means that we are currently at the equivalence point. Now the quick and dirty way to have seen that was the same volume, 100 mils, of the same concentration, 0.5, but this is a more precise way to think about it. That will always work, doesn't rely upon you recognizing same volumes and same concentrations. Anyway, at the equivalence point, when we neutralize a weak acid, we make its conjugate base. So therefore, at the equivalence point, we only have the conjugate base. In other words, the pH less than 7. Absolutely need it drilled in your head. Neutralize a weak acid with a strong base, equivalence point pH greater than 7. Neutralize a weak base with a strong acid, equivalence point pH less than 7. Determine the pH in which 40 moles 0.2 molar aqueous acetic acid has been titrated with 20 moles of 0.2 molar NaOH. So at A level, in many boards, you don't have to do these calculations, but this actually, you don't need to do a detailed calculation. You need to recognize the following. First of all, what's the new concentration of the acetic acid at this point? Well, it was 0.2 molar, and you had 40 mils of that, but now you've added another 20 mils, so you've diluted it. So the acetic acid, even with the reaction, is 0.133 molar. Sodium hydroxide, you have 20 mils of 0.2 molar, but you've diluted it with another 40 mils, so now you've got 60 mils. So that concentration is 0.0666. And what you need to recognize is that this is half of that. In other words, you're at the half equivalence point. The other thing you could have noticed is 0.2, 0.2, so same concentrations, half the volume, half equivalence point. The half equivalence point, pH is pKa, so therefore the pH is minus the log of Ka, 1.8 times 10 to the minus 5, 4.74. So be very, very aware of that. First important point of titrations, as we illustrated with the last question, what's the pH of the equivalence point? Second important thing, when you are titrating a weak acid with a strong base, the pH at the half equivalence point is the pKa. Lovely little question. I got it from an ACS paper, but I think either somebody pinched it from them or they pinched it from somebody or copied it, because I've seen it several other places. But very nice question. So we got 3 stages in the titration of HOCl with KOH. Now let's have a look at what we got here. Okay. O is usually red. H is usually white, so we got HOCl, so presumably Cl is green, and then the other thing that's floating around in the place is potassium, presumably those are the purple ones. Okay, so always identify what the little color key might be. Now, if we look at B here, all we've got is HOCl. That's the only thing that's in there, the reactant, HOCl. So in other words, B must be at the start. Okay, now then we start adding in some of the KOH, and as we do that, the HOCl gets turned into OCl minus. So here's an OCl minus, for example, and a water, so there's water, and there's K plus, so there's a K plus. Okay, so what we see in this one here is we've still got some HOCl, but we've also got some OCl minus, we've got some water and potassium. We go up to C, there's no HOCl left anymore. All 4 of those HOCls have been turned into 1, 2, 3, 4 OCls. We got 4 potassiums, 1, 2, 3, 4, and we got 4 waters. So this is at the start. This one here, we've still got 2 HOCls left. So this must be during the titration. We've still got some acid left in there. Okay, and then we got the OCl minus, so we got some base, and indeed this is actually the halfway point of the titration. And then we get up to C, right, still during the titration, but now we got no acid left at all. All we've got left in there is the conjugate base, and then of course the water and the potassium. So this is actually at the equivalence point, because we only got 4 potassiums and 4 waters in there to match up with the 4 of the acids with which we started with. Okay, so therefore here at the start of titration, we've only got the acid. It's going to be the lowest pH. Then we keep adding base, half equivalence point, so a higher pH. Keep adding the base, get rid of all the acid. At the equivalence point, this is the highest pH. So therefore, in order of increasing pH, B less than A less than C. Consider titrations, 250 moles, 0.3 molar CH3COH, that is a weak acid, and HCl, that is a strong acid, titrating both with 0.1 molar NaOH. Well, let's think about what we know about these things. Okay, we've got the same volume. We got the same concentration, so we have the same number of moles. Okay. Now, strong acid is, of course, much lower pH than a weak acid, so the initial pH is not going to be the same. pH at the equivalence point. Well, when you titrate a strong acid with a strong base, the pH is 7. When you titrate a weak acid with a strong base, the pH is greater than 7, so these will not be the same. The volume of NaOH needed to reach the equivalence point. Well, the equivalence point is where you got the number of moles of NaOH is equal to the number of moles of acid. And because we have the same concentration and the same volume of each of those solutions, we got the same number of moles. So even though the different acids, one weak, one strong, because we got the same number of starting moles of the acid, we're going to need that same volume of NaOH required to get there. So I like that. And how about the pH when exactly 100 mils of NaOH has been added? Well, you got a strong acid, which is going to not change as quickly as the weak acid does. So therefore, the pH for the strong acid is always going to be lower than the pH for the weak acid until they've all been neutralized. And when we've added 100 mils of 0.1 molar NaOH, that's certainly not enough to neutralize 250 mils of 0.3 molar of the acids. Kind of a clever question. I hope I explained it well enough for you to understand. So titration of weak monoprotic acid, solution of sodium hydroxide, known concentration. What quantities are equal at the equivalence point? Well, at the equivalence point, what's happened is that you've added exactly enough moles of OH minus to neutralize all the moles of acid present at the start. Of course, actually, it's you've added enough hydroxide ions to neutralize all the starting molecules, but instead of talking about individual ions and individual molecules, we put them together as moles. So it's the moles that is important, nothing else. Now, as we go through this, A talks about concentrations. No, nothing to do with that. B talks about moles of hydroxide. Oh, that's good. But moles of hydronium ion. No, it's not moles of hydronium ion. It's moles of acid. Okay. Volume and volume. Nah, volume's rubbish. Concentration and concentration. No, rubbish. How about here? Moles of hydroxide ion and moles of acid initially present. That looks pretty good to me. So the answer, wading through all that verbiage, is E. At the equivalence point, the moles added is equivalent to the moles with which you started. Now, important, that last question, we said monoprotic acid, because here we're talking about a diprotic acid, H2A, for which I give you 2 Ka values. So let's think about titration of a diprotic acid. We start with the diprotic acid. We add in some of the base, get halfway, so half equivalence point, and then we add that same amount again, and we got the equivalence points. And ordinarily, that's the end of it, the interesting bits from monoprotic acid. But the whole point is, this is just where we've taken care of the first proton, but when we got a second proton, we have to do the same thing again. Okay, so in that second one, there's that next equivalence point. And of course, halfway between the first equivalence point and the second equivalence point is that second half equivalence point. Okay, now the crucial thing about half equivalence points when you're talking about weak acids is that the pH at the half equivalence point is the pKa. So here was for the first proton, half equivalence point, pKa. Here's for the second proton, half equivalence point, pKa. Also pKa1, pKa2. Okay. Now, in terms of volume used, and I'll animate this in a minute, it takes the same volume to get to the first as it then does again to get to the second. So if this is VEQ, this was VEQ over 2, this was 2 VEQ, and this is 1.5 times VEQ. So with that and all, let's see what we got. Ka1 is 1 times 10 to the minus 6. So therefore the pH at this first half equivalence point, which is the first Ka, is minus the log, that's the P of Ka, which is 6. Okay. Then up to this second equivalence point. Well, now this is the pKa2, so that's the second proton. So Ka2, 1 times 10 to the minus 10. So P of that is 10. So that P is 10. Okay. So how much of the sodium hydroxide do we need to get to a pH of 10? Well, it's going to be 3/2 the equivalence point. Okay. At the first equivalence point, moles of acid is moles of base. The acid is 50 moles times 1 molar. The base is however much X was times the 2 molar. So the volume at that first equivalence point is 25 mils. So 25 mils to neutralize the first, 50 mils to neutralize the first and the second. This would be 12.5 mils to neutralize half of the first. So this here to neutralize all the first, 25 mils, plus half of the second, another 12.5 mils, is going to be 37.5 mils. Easy when you've seen all the pictures, tough to talk through it. Hopefully you followed that one okay. So now we've got an indicator question. Remember, the big thing with indicators is they change color around the equivalence point. So if you're asked to determine which indicator, you just need to know something about the equivalence point. So if we look at the question, 20 mils of an aqueous solution of ethylamine. Well, the 20 mils is probably not an important piece of information. Ethylamine is, because that is a weak base. Titrated with 0.3 molar, again, probably concentration not too important, but the fact that it's HCl with the strong acid is very important. Now, when you start doing this titration, you get a neutralization, and when you neutralize a weak base, you make its conjugate acid. And we know the conjugate acid of CH3CH2NH2 is CH3CH2NH3 plus. Okay, and we're told the Ka for CH3CH2NH3 plus is going to be rather big for pKa, which means this is a rather weak conjugate acid. Now, we know the equivalence point, all the equivalence point is you're only going to have the conjugate acid. So we need an indicator that's going to change color around the pH of a solution of the conjugate acid. So 10 to 12, useless, that's basic. 8 to 10, useless, that's basic. So we're going to either use bromocresol green, which is a color change for a very weak acid, or thymol blue, which is a color change for a good, strongish acid. Well, this got a pKa of 10.75, so it's an extremely very weak acid. Therefore, we're going to want to use bromocresol green, which is going to change color in the weakly acidic region. Summative question 40, titration of a weak acid, this time with a strong base. You want an acid-base indicator that changes color in the pH range. Well, if it's a weak acid and a strong base, again, you want the color change around the equivalence point, weak acid and strong base. You are going to have only the conjugate base left at the equivalence point. So we want the pH of the indicator change to be greater than 7. So not 2 to 4, not 5 to 7, not probably 6 to 8. So do we want 7 to 10 or 10 to 13? Well, again, in order to determine which of those basic regions we want, we need to figure out how good is the conjugate base. Well, the weak acid has got a Ka of about 1 times 10 to the minus 4, so that makes it a pretty good weak acid, which means its conjugate base will be really weak. And if you remember, Ka times Kb is 1 times 10 to the minus 14. So it's Kb 1 times 10 to the minus 10. So a solution of the conjugate base is only going to be weakly basic. So therefore, probably the 7 to 10.